Okay. We covered up to the gradient-based approaches, which is usually which are usually used in the computer vision, the vision field, the video field. Well, not particularly video field. I haven't seen anything. I haven't seen any interpretability issues in the videos. I guess there should be, but it's that I'm not just the video guy. So yeah, we looked at some of the 3 examples, the 3 approaches based on the gradients. So one is the first one is not really related to gradient. It's to visualizing the activation maps. I mean, activation of the intermediate layers. Another is synthesizing your inputs so as to maximize the specific node or specific output node. And the third was class activation map, the one with the elephants. So that's, yeah, okay. So that will be the wrap, and then we'll turn to neural attentions. So any question, like anything related to previous classes? No, we're good to go. All right then. So neural attention. Okay, so attention mechanism or neural attention. It's a concept pretty old by. I mean, when I say old, it's old by AI standards, because the machine learning field progresses so fast. Like something 5 years old, it's already old. So it's not like mathematics. So neural attention, it was introduced in a paper named Neural Translation by Jointly Learning to Align and Translate. So it's a very famous paper presented in iClear 2015 by Badenau, Choi, and Bengio. So they're all very famous names. It was proposed to do English to French translation using RNN. So it's a sequence-to-sequence model. I guess, yeah. So in iClear 2014, there was the very first sequence-to-sequence neural translation paper. And then this is kind of like a follow-up where they add the attention mechanism. And the gist of it, the essence of this paper, the attention mechanism, is that they want to use hidden layers from all time steps when making prediction. So just to illustrate, let's say that you are predicting something. So this is not particularly a translation example, but anything. It could be like the character RNN that we did. Oh, by the way, did anybody try out the character RNN Python notebook? Or any question related to Python? PyTorch, the PyTorch example? Nope. As I said, the next assignment will be based on the Python notebook that I shared. So I hope that everybody at least look at the codes. I mean, just run it. They don't have to like change it, but at least run it. Set up the environment. Anyway, okay, so yeah, this is just any generic prediction example using RNN. So there's like 10 time steps. You're feeding either 10 visits, 10 hospital visits, and trying to predict the future heart failure, or maybe you're feeding in 10 characters, like names for like origin prediction. Like you're feeding in like Johnson, and then you're trying to predict its origin is English, something like that. And then typically what you did is you accumulate all the information on the final hidden layer, H10 or HT to be more general. You've put all your information into the RNN, and you assume that the final layer, H10 or HT, contains every single, like all the information from the past. Like it is like the representation of the entire sequence, and then you use that. You put that H10 or HT into the logistic regression to make a binary prediction, or if you put it through a softmax, then it's a multi-class classification. That was your setup. But in neural attention, what they do is they want to use all the time steps, like starting from H1 to H10. They want to use all the time steps, because when you start feeding in a lot of like a very long sequence, like here in the example, we're just feeding in 10 time steps, but in practice, sometimes you feed in like, I don't know, 100 time steps or 200 time steps, and then sooner or later, the RNN will start to forget what happened in the very early stage. For example, like you can't assume that H200, for example, will remember every single detail in H1 and H2 and H3 and H4, because it's like a long time ago. So this example is this neural attention rather explicitly tries to use all time steps, like from H1 to H10, and the way they do it is they combine it. Well, they use a convex combination of all the time steps. So these alphas are the attention weights, and you have alpha 1, alpha 2, like corresponding alpha weights per time step. So for H1, there's alpha 1. For H2, there's alpha 2. And for H10, there's alpha 10. And then you multiply them, and then you weight sum them, and then you get C, which is usually called a context vector. Nowadays, they don't use this name. They're very often, but back in the days in 2015, this was called a context vector. So the context vector can be represented like this: is alpha 1 times alpha 1 H1 plus alpha 2 H2, something like that. And then it's a convex sum. So alphas, all the attention weights should sum to 1. So alpha 1 plus alpha 2 all the way to alpha 10 should be 1. And so the next step is you need to define alpha 1. So no, before that. So yeah, you have the context vector, you derive the context vector C, and then you put that through either logistic regression or softmax, and then you make the prediction. So what's good about the neural attention is, first of all, you explicitly combine all the hidden layers from all the time steps. So you don't have to, you're not forgetting anything. So that's why it outperform. So when it was first introduced for translation, it did outperform the previous one, where they don't use attention mechanism. And but what is in this class, where the topic is interpretability. So attention, what it's good for is that it can be used for interpretation, or getting an insight into what's happening under the hood, what's happening to the model under the hood. So alpha 1 all the way to alpha 10 denotes the usefulness from each word. You can, because it's a context sum, so you can't have like 100 here, 100 here, 100, 100. You can't assume. I mean, your attention cannot put equal amount of attention, like strong attentions, on all time steps. Like something has to be stronger, something has to be weaker. So it means that the model has to pay attention to a particular time step. So so you can, and that kind of like indicates the usefulness or the importance of a particular time step. For example, if alpha 2 was like 0.9 and all the others were like 0.1, 0.01, 0.01, 0.01, then it means that the alpha 2, there's something very important happening in alpha 2, or time step number 2. So that's why alpha 2 is like 0.9. So it can be, it indicates the importance of a specific time step. And as I said, so the attention weights should be defined. You can't, and it's defined automatically. You yourself do not define like, okay, I'm gonna put like 0.9 here and 0.1 here. You don't do that. It depends on the example, like the sample given to the RNN, and based on that, the alpha weights will be determined by a separate attention function. So you usually use attention. I mean, so like these days it's all like transformers and BERT and all that. But back in the days, what they did is there's an RNN for encoding the sequence. So the sequence itself, like the characters of your name, or the visits of your individual visits of the patient, like they will be processed by an RNN, like original vanilla. I mean, no, not vanilla, like GRU or LSTM, like typical typical RNN variants. And the attention weights, these alphas, will be coming from a separate neural network, typically feed for a neural network with like a couple of hidden layers. And so it's just let's call it, so this is just a simple feed for a neural network with a single hidden layer. So there's the input layer, there's the hidden layer with, could be sigmoid, could be ReLU, could be tanh, and then the output is just a regression. So there's no sigmoid here or tanh here. There's no ReLU. You can, it's just a linear operation of H. So the output would be ranging between the negative infinity and the positive infinity. So let's call this function where you put something in and then you get a scalar value out. We'll call this function AX, A for attention. So, and then the X, so at every single time step, you will put your input into your attention function, and then you'll derive certain scalar value. So x1 being, again, it could be a visit, could be a character in your name or whatever. So each time step, each input, each input in each time step, you feed it into your attention function A, and then you get some scalar value out, as I said, like some value between negative infinity and positive infinity. So all the y's, like y1 to y10, will have some scalar value, and they're unnormalized, but you want the alphas to sum up to 1. You want the alphas to be a convex sum. So you put it through, you take all the y's and then put it through a softmax function, and then that's how you get alpha. Because softmax function is a probability. It converts a bunch of number into a probability distribution, like a multinomial distribution. So when you put all the y's into the softmax, then the corresponding alphas, like alpha 1, alpha 2, will be now like a probability value. And that, yeah, so like this, like the softmax function ensures that all the alphas will sum to 1. And you can, well, in this example, I explicitly put x into the attention function and derived y. But what typically you do in the RNN setting is you put x's into your RNN, and then you get the hidden layers, H, like H1, H2, like all the way to H10. You put those H's into the attention function. So instead of putting your input directly into your attention function, you typically put your hidden layers, hidden representations into your attention function. It's actually, yeah, it's up to you. It's designer's choice. Whatever works for you, whatever actually gets you the best performance, this doesn't matter. But it's all like machine learning, you can do whatever you want, unless you're cheating, then unless you're except for like cheating, as long as you get like good performance, then that is actually the best practice. So, but what I'm saying is typically what people did back in like 2015, 2016 is they feed the input into the RNN, derive the hidden representation for each time step, and then put those hidden representations into an attention function, derive the alphas, and then get a convex sum out of the hidden representations. Right. Okay. So the good thing about attention is that it indicates importance or usefulness of each of inputs at particular time steps. So yeah, this is because they're doing translation. This should be 2015 actually. So they're doing translation from English to French. So here, this is English side, this is French side. So English is the destruction of the equipment means that Syria can no longer produce new chemical weapons. Period, end. And the corresponding French sentence is something like this. And what's happening here is that each you first feed. Okay, in case there aren't some people who's not familiar with the sequence-to-sequence model or encoder-decoder framework, let me just quickly draw what's happening here. So there's x1, there's x2, all the way to x, let's call this xt, and you put this into your RNN. Then you get H1, H2, HT, and then in the like very, very early form of encoder decoder model would be you get HT, and then you use this HT to decode. I wonder what they use for back in the day. Like maybe it was S0. No. S1 all the way to S T. Yeah, we can call this T prime. And then there will be your output, Y1. Y2 all the way to YT prime. And typically your Y's, I mean, yeah, I didn't write the, oh, actually there should be, because this is RNN, so there should be arrows here. So what's happening here is you're feeding in a sequence of length t, and then you're trying to like generate a sequence out which has the length t prime. So this is a very nice framework for like translation. You feed in English words here, like a sentence, like destruction of all the way to like end symbol, and then you want to get out like la destruction all the way to end symbol. And so this is like a typical very early form of attention, early form of sequence to sequence. And what you want is you want these Y's to be the correct sequence or correct French sentence in this case. And you typically feed in like feed in the true. So this will be your prediction. But what you do during training is you feed in the true previous word, Y1, and like. Well, yeah, this, yeah, you feed in the previous one, so S, Y, T prime minus 1. This should be actually 0. So this should be 0 actually. Okay, I messed up the time indices, but anyway, so you get the point. So what happens is this, and so okay, so there is no attention mechanism here, but if we throw in the attention mechanism, then what happens is every time you try to predict like a corresponding French word like la destruction, something like, for example, when you try to predict this, you pull all the way, you pull all the H's like H1 to HT. You use a convex combination to predict Y0. And then when you move to the next step, you use attention mechanism. You do a convex sum of H1 all the way to HT to get Y1 again. And like repeat that process for every single YI's until you get to the final point. So that's what, and of course you can imagine that every single time you predict YI, the attention distribution or the alpha weights will be different. Like when you're predicting la, and when you're predicting destruction, the attention weights will be different. So that's what's happening here. So so you fed the entire English sequence into your RNN, and then you're trying to predict la. And when you're trying to predict la, the attention distribution is like this. so the brighter the brighter, the stronger the attention weight. So all the attention is being poured towards destruction when you're trying to predict law. And then when you move on, and then when you're trying to predict destruction, the French word destruction, again, all the attention is focused on destruction. So it makes sense. A lot of destruction means just the destruction. So the two words should be like derived from this corresponding English word, right? And then I don't know French that much, but just to look at some very easy tokens like this. Like this looks like equipment. Of course, like the same word here. So you can assume that when the RNN, the decoder, is trying to predict the French word equipment, then of course all the attention should be focused on the equipment English word. There are some interesting exceptions, or maybe not exceptions, but like I don't know what this is. Pew, whatever. All right, Syria is Syria, but this has equal distribution, equal attention distributed both ways here, like here and here. But I don't know. I'm not a French. I don't speak French, so I'm not sure if that's actually the correct attention to be pointed to. But anyway, so yeah, this was one of the figures from 2015, the very first neural attention paper, and this kind of like gave people the idea that hey, maybe we can use attention not just for boosting your performance, but actually to get a sense of what's happening under the hood, what's happening to the neural network model when it's trying to predict something. All right. So this is more of a philosophical question, but some people are tackling this very specific problem where they want to figure out if attention is truly an explanation, or if it is an explanation, what does it explain? Like, how much can we trust what we see from the attentions? And it's not, first of all, it's not same as the coefficients of the logistic regression, where each coefficient or each weights in the logistic regression model indicates the correlation between the corresponding feature and the output. For example, as I said, like if a certain coefficient or weight, like the ith weight of logistic regression is positive, then that means the ith feature is positively contributing towards the final prediction. If ith weight is negative, then the ith feature is negatively contributing towards the final output, the final prediction. The attention is not the same. Like even if something gets like high attention, like attention can only be non-negative, because you're putting your attention, in order to get your attention, you need to use softmix. So there can't be a negative attention. So all the attentions are positive, at least like non-negative. And just because some like token or some ith step feature input has a positive attention or strong attention, doesn't mean that it is positively contributing towards the final prediction. It just means that something's there, something is like useful in the specific time step. So it's definitely less of an explanation compared to logistic regression weights, but still it is something. It's like some explanation, and people don't know what exactly, like the nature of its explanation, what does it truly explain? So yeah, there's some couple papers, very interesting papers from EMNLP, I think, last year and the year before that. Something, I think the title was "Attention is Not an Explanation." Yeah, I think that was the exact title. So the authors try to well, I guess you can say that it's kind of like an attack on the whole attention thing. Like attention doesn't really tell us anything. Like attentions are not explanation. And then there's a follow-up paper in 2019 EMNLP titled "Attention is not an explanation." So it's like a refute on the previous paper. So and that paper is trying to describe that attention can mean something. It's not totally like it's not a total bullshit. It's something, there's something there. So it's still an ongoing topic. People like it anyway because it's very, I mean, look at this picture. It's very intuitive. It's very straightforward. Like something's like when you're predicting something, some attention is being like poured towards a certain time step, and it does seem to make sense. So people like attention. All right, so moving on to the to how we can use it in the electronic health settings, electronic health record setting. Any questions so far? Anything related to attention? Nope. All right then. Right. So what do we have here? Yeah. Okay, so if we can assume that if we're trying to do a heart failure prediction, just like before, so there's like sequence of visits, visit 1, visit 2, visit 3, and different things happen in each visit. And instead of just feeding these visits into the RNN and then using the final time step H3 in this example, if instead of just using H3 for doing binary classification, like for like binary heart failure prediction, you can assume that you can imagine that if you use attention mechanism on top of this, then you're mixing or you're combining explicitly all the visits like H1, H2, H3, and that can indicate the importance of a certain visit. Like if all the attention was being focused on, for example, visit 1, H1, then it kind of indicates that something happened in visit 1 that really really pushed the model to predict make a certain prediction, right? So that would be kind of an indication, like an indirect explanation, something like that. But we want to do something better than that. So what the motivation behind retain the model that I'm going to introduce today is, first of all, the attention is not a correlation, it's not exactly the same as the logistic regression weight. It doesn't mean the contribution towards final prediction. It's just importance or usefulness. So we want to turn that around. We want to use attention, but we want to use it in such a way that it actually becomes the contribution towards final prediction. So that's one. And another is that because it's a two-layer architecture, there's a two-layer structure. There's a sequence of visits, but within each visit, there's like different number of set of codes. So we need more than just a sequence level interpretation. Just saying that visit 1 was important is not enough. So we want to do better than that. So, all right. So, okay. Just a recap in case anybody has forgotten what it is like to use what it is like to feed in electronic health records into RNN. So we have, this is a typical architect. This is typical structure. Visit 1, 2, 3. Different number of codes per each time step, and then you can represent each visit I as a multi-hot vector. It's like this is counterpart of one hot vector. So it's like a binary sparse vector with typically several dimensions set to 1. So like this, just like this. So this will be your visit representation, and then you put it through a embedding layer to make it into to project it into the lower dimensional space. You get V1, which is the visit embedding now, and then you put that into your RNN. So then the H1 will now represent the visit. I mean, yeah, V1 and H1 are typically probably the same, but if you start putting in more like this, like you put V1, V2, V3 all the way to VT, the final visit, and then hidden layer of HT will be contained. Theoretically, it'll contain the information from all time steps. So that was, and then you put it through either sigmoid or softmax. So that was a very quick recap of how to feed in electronic health records into RNN. Right, so moving on to retained. So the motivation is, let's use neural attention to make a fully interpretable sequence model. So not just like indicating usefulness or importance, but actually making a full interpretation using neural attention. All right, so I guess everybody will after they've done homework assignment 3, they will realize that RNN is way more powerful than logistic regression. Yeah. Yeah, well, so this time the assignment number 2 was hospital readmission, and we used a single, right? I guess we can't make a direct comparison between logistic regression and RNN when we're doing hospital level readmission prediction. But anyway, so when I first used RNN for predicting heart failure with based on the electronic health records, it like quite a big margin, it outperformed like classical models such as like support vector machines or logistic regression, and even neural network with a single hidden layer. But like performance itself is not enough in a lot of cases in medical domains, because it's really hard to convince doctors to believe in a model that doesn't explain itself. Like zero accountability is not a good, like model with a zero accountability is probably not going to sell itself to like physicians or hospital administrators, and it'll never be deployed in the real world because you can't really trust what's happening there. So like naturally the next step was to make a interpretable model. So like this is a typical scenario. If your heart failure prediction model based on the RNN model predicts a score 0.9, which is a really, really high score. Like 0.9 is like exceptionally high. It's exceptionally risky patient. And maybe people would be interested in asking question like, if the score such as high as 0.9 was produced by the model, then was it because of the cough at visit 1? When I say cough at visit 1, was it because of this, or was it because of this, or was it because of this? Like you can't really know when you're using RNN, because all these informations are like mixed and summed up in the final hidden layer HT. So if you remember the update equation for each I in the RNN, it is a non-linear. You linearly so how can I say this? So you linearly convert your input and you linearly transform your hidden layer, and then you sum them, and then you put it through typically a 10H, a nonlinear activation function. So, and you do that every single time. So you can see that all these information will be going through a lot of nonlinear operation, nonlinear transformations up until HT, which means that it's really hard to decompose and try to like backtrack your final output prediction. It's hard to backtrack from there to individual like XTs, XT, X2, X1, and see the like trying to justify why your score is 0.9. Like you can't, and when you ask these questions, you can't really answer them with vanilla RNN or even GRU, which is even more complicated. And so is the case for LSTM. So as I said, we should ask 2 questions when it comes to EHR, because it's a 2-layer structure. So one is, which visit contributes more to the final prediction, because there are multiple number of visits, like starting from H1 all the way to HT. Second question is, in specific visit, what particular code or what particular concept contributed towards the final prediction? Because as I said, there can be different number of things happening in each visit. For like in our early example, there were 4 things happening in V1, and I mean something should be more important for predicting heart failure. Like IV fluid, probably you can imagine not so much, but maybe cough has something to do with it, and you're not sure. So we want to answer this question too. So two questions. One is which time step is important, and which code within that time step is important. So two questions. So we can assume that we should, it's naturally you can assume that we should use two separate attention mechanisms. One on the visit level or the sequence level, and one on the code level. So two separate predictions. Two separate attention mechanisms. All right, give me a second. Let me just pour some water. Right. Before we get into the architecture, the mathematical derivations, and how we can decompose like all these like rather boring stuff, or maybe interesting for some people, we can start with some interesting demo, the end product of what we can do with retains. Actually, there was a chat. Could you give me just 1 second? I'm trying to see. So the attendance have gone up. So just. All right, give me just like 2 minutes. Interesting. Oh, okay, I see. All right. Okay, the question was, how about define xi as integrated sample from x0 to xi? Let me see. What does that mean? How about define xi as integrated sample from x0 to xi? Does that mean that we don't use RNN, but use something else, or? Okay, let me just discuss this real quick in Korean. So 그 재영님, 이게 무슨 의미신가요? XI를 X0부터 X이가 적분한 거라고 하면은 RNN을 쓰지 않고 뭐 뉴럴 ODE 같은 거 말씀하시는 건가요, 혹시?
아니요, RNN을 쓰는데
네.
그 인풋 XI에 들어가는 게
네.
I 번째 인풋을 이제 뭐 X 프라임 I라고 하고
네.
그것을 뭐 첫 번째부터 I 번째 샘플까지 누적한다 치면은
네.
우리가 뭐 기침을 자주 하는데 지금까지 통계를 쭉 봤을 때 기침을 계속 해왔으니까 그거의 가중치를 높여주고 저번까지 기록도 같이 이렇게 반영해서 RNN하고 같이 하면 그런 혹시 아이디어 하기도 그렇지만 그런 경우가 그런 식의 반복 접근을 할 수 있는가 해서.
그러니까 예를 들어서 기침을 했으면은 계속 어떻게 되는 거지?
계속 해왔으면 이렇게 뭐.
그러니까 새로운
샘플.
인풋을 넣는다는 거. 그러니까 이제 과거에도 기침을 해왔다라는 새로운 인풋을 넣는다는 건가요?
뭐 그런 식으로 이미 RNN에 적용이 되어 있을 거 생각하지만. 네. 인풋을 넣는 샘플도 또한 저번 샘플과의 지난 샘플과의 관계를 고려해서 더 업데이트를 치면은 이런 그냥 RNN 2번 도는 느낌인데.
약간 그렇긴 하죠. 예를 들어서 이 사람이 매 타임스텝마다 예를 들어서 기침 진단을 받아가지고 이제 매 타임스텝마다 기침 RNN에 넣었고, 그다음 요 번째 I 번째에도 다시 이 사람이 뭐 예를 들어서 뭐 과거에도 기침이 있었다라는 식의 인풋을 넣는다면 새로운 인풋을 정의해서 그냥 기침이 아니라 기침을 오랫동안 해왔음이라는 새로운 코드를 만들어서 넣으면은 사실 중복되는 셈이죠.
아니 뭐 기침가스 막 1이 아니라 더 큰 값을 그런 것도 되나 싶었는데.
예, 그렇게 할 수도 있어요. 맞아요. 예.
어,
근데
네.
RNN이 만약에 이론적으로 RNN이 제대로 일을 하고 있다면 굳이 그럴 필요는 없죠. 그러니까 이제 얘가 과거의 걸 잘 기억을 하고 있다면 굳이 이제 이거를 그러니까 이미 과거에 그동안 계속해서 기침을 해왔다는 걸 이미 RNN은 알고 있어야 되잖아요. 그동안 계속해서 지속적으로 그 매 타임스텝마다 기침이라는 코드를 넣어줬으면은. 그러니까 거긴 근데 I번째 굳이 이 사람은 뭐 기침 증세가 심해졌다 그건 또 다른 얘기인데 그게 아니라 단지 그냥 이 사람은 오랫동안 기침을 해왔다는 정보를 이렇게 명시적으로 넣어줄 필요는 없다는 거죠.
감사합니다.
네. Okay, so to summarize the question, or summarize my answer actually, is that if, uh, if we assume that the RNN is doing a good job of tracking so far what has happened from like time step 0 to time step I, then there's probably no like need to explicitly feed in the information that in the ith time step that the same thing has happened over time again, like over and again, over and over and over again, because already RNN would remember the past. I mean, ideally, it's not always the case. So maybe you can get a few like very small marginal improvement by doing like providing explicit information at each time step, but I wouldn't say it's would make a significant difference. All right, so okay. And yes, interestingly, this notion of viewing xi as an integrated sample from x0 to xi is probably the essence of the neural ODE paper, the neural ODE idea, which is a very new framework. I'm hoping that I can try to go over neural ODE at some point, like maybe when we're talking about time series explicitly. After the first half of this course, I'll spend most of the time trying to address different modalities, like how to deal with like medical images, how to deal with like text, how to deal with time series such as like what's it, like EKGs or EEGs, or maybe your blood pressure, something like that. And in that case, neural ODE is probably like a very nice model to apply. And the essence or the core idea of neural ODE is that maybe we can view xi as the integration like an ordinary differential equation, like 미분 방정식. So I mean, yeah, this was a very interesting question in that regard. Anyway, but we won't talk about that today. Okay, so the end product. Can everybody see the website? Wait, what am I sharing now? New share. Okay, yeah. Okay, now. Right. Okay, so can everybody see the website now? It's a very crude demonstration. I mean, crude visualization. The visualization quality is like. All right, so. Oh, good. Can everybody see this? Okay, cool. Yes. All right. So what's happening here is the X. So it's a single patient. It's a patient ID something. So it's de-identified, of course. And this patient actually ended up having heart failure. So the x-axis indicates the number of days since the start of the observation. So, and this vertical line here is when the patient was diagnosed with heart failure. So in this specific line, like 490 or 485, this is when the hospital, I mean, this is when the patient visited the hospital and then the doctor said, okay, you have heart failure, so we need to treat this. So that's when that happened. And the y-axis is the contribution. So it's not attention strength, it's actual contribution score. And what that means is, so there's a cluster of dots here. Like there's a dot group here, there's another dot group here, another here, and each cluster indicates a single visit to the hospital. So this is like the very first visit, second visit, third visit, fourth visit, fifth, sixth, seventh, eighth, all the way to like 20th, maybe. Sorry, excuse me. And of course, in each visit, there are a lot of things happening. So here, the red dot here is, oh, I can't actually, okay, yeah, I can actually, okay. So one is the first, here I think 3 things are happening in day 200-ish. Ulcer drugs. So the patient was prescribed ulcer drugs, 위궤양, 위궤양 약, diuretics. This is something related to your blood pressure, 고혈압약, and antihypertensive, again, something to do with your blood pressure, and cardiomyopathy. So what is that? So it's yeah, I don't know what that means in Korean. Cardiomyopathy. Something to do with your heart. Oh, by the way, some students might have already seen this demonstration when I was doing like a seminar, AI grad school AI seminar for like I think that was last week. But at least all the neighbor people and all the international students have missed this. So let's just go through it very quickly. So as I said, so these indicate the clusters indicate the individual visits, and you can see some are higher. Like for example, these are higher in the y-axis, and some are lower. They are located in like near the 0 point. So what they mean is the contribution. So Retain can exactly calculate the contribution of each event or each code towards the final prediction. So here you can see that this one, so D means diagnosis. So cardiomyopathy in the very last visit contributes most towards the final prediction of heart failure, where the score was 0.34. So this has like a very high contribution portion when the model is predicting 0.34. And you can actually do this step by step. So let's just go through that. So what's happening here is I'm feeding individual visits to the retained model one at a time, and the risk score is changing as we feed new information. And of course, the contributions are recalculated. And the green ones are like the negative contributions. So it means that when they're like very irrelevant, or they negatively contribute towards the risk score. So initially there were a lot of heart-related stuff, and then in the intermediate phase, not so much. Seems like the patient's doing well, and towards the end, the patient starts to like get the heart-related conditions again, and then finally, like turns into a very severe pain, develops a severe heart-related conditions like lower respiratory disease. So it's like heart failure. When you have heart failure, it's hard to breathe. So it's not about your heart only, but it's like there can be like fluid in the heart, or like fluid and it's hard to breathe, and you get like it's very like you get fatigue all the time, and then in the end you get cardiomyopathy. And right after this, so this was like the last visit before the patient was diagnosed with heart failure. And what happened here is that, so as you've seen this progress, certain things were high, or had a higher contribution, certain things were not. And it's of course things that are related to heart, like lower respiratory disease, cardiomyopathy. I think there was atherosclerosis, which is 동맥경화. And so all these like very heart-related symptoms have a higher contribution compared to something totally irrelevant, like skin diseases, like dermatological. I think there were a lot of skin diseases somewhere. Yeah, skin disorder. Like they have minimum, like all none to zero impact towards the final prediction. And interesting thing is I've never explicitly trained or guided the model or regularized the model to focus on the heart-related codes. I've never done that. It's just that the model picked up the signals and the model understood that in order to properly or correctly predict heart failure, I need to pay attention to, I need to like focus on the heart-related symptoms. So that was interesting. Another thing is, if you look at these codes like cardiomyopathy here, I think there was cardiomyopathy here and also here and over here. So they're all the same codes, but the recent codes are contributing more towards final prediction compared to the codes in the past, like here, or maybe in the very beginning. Like, so it has understood the concept of time. So even if the same information, same codes happen, the ones that happened more recently should count more towards final prediction. And again, I didn't tell the model to focus more on the recent, like I didn't tell the model to tell the model that like recent information is more important to like old information. It's just that the model has picked up that signal. Like in order to accurately predict the risk score, I need to pay attention to recent information. So two things were interesting to me. So with Retain, you can do this kind of stuff. So like the accuracy of your prediction is pretty up there with like vanilla RNN. So it's almost as good as the GRURL STM. And you can also completely fully interpret or fully decompose the contribution scores into like individual code level, not just the visit level, but every single code and every single time, every single visit, you can exactly calculate how much each individual codes contributed towards final prediction. All right, so that's what we're gonna try to build here. All right. Any question related to the demonstration so far? Nope. All right, so we've got 30 minutes. I guess we can finish up Retain today. All right. All right, let me just like take a rest for like 2 minutes. My throat is really raspy as hell. We've got, all right, so we have Retain today, and then Model-Agnostic approaches. Wow. All right, let's get back to the material. Okay, so two attention mechanisms to focus on the visit level importance and the code level importance. So this is the architecture, the comparison between typical architecture when you want to use RNN with attention mechanism, and this is how we do it in the Retain model. So again, this is like very classic. Now that everybody's using transformer, at least in the NLP world, natural language processing. I haven't seen a lot of transformer in the medical domain, interestingly. Yeah, I guess we can talk about why that is. I have some like explanation, but unless everybody knows what transformer is, I can't really talk about it. So okay, anyway, so this is back in the days like 2015, 2016. So this is like the standard way to use RNN with attention mechanism. So here, there's RNN here, and what's happening is there's xi, so there's x1, x2, x3, all the way to xt, and so this depicts what happens in a single time step t, or I, to be correct. So in I time step, you put your input, could be a visit, could be a character, could be a word or whatever, and then you put it into your RNN, and then so there, in order to indicate that it is an RNN, there's like a self loop here. So you put this into RNN, and then you encode it into the hidden dimension H, or in this case V, to denote the visit, and then using that hidden representation, you put it through a single feed-forward neural network, the attention function, to get the attention weight of that time step, alpha I, and then you do that for all time steps, so you get alpha 1 to alpha t, and then you combine the hidden representation with the alpha. You do a convex sum to get the context vector here, and then you get your final output y. You can do it for like each time step, or you can do it for the entire sequence. Like if you do it for each time step, then you're trying to like predict for each visit, like will this patient die in this visit or something like that. If you're doing for the sequence, then you're doing like heart failure prediction, like given all time steps, you're trying to predict whether this patient will have heart failure in the future or not. But to make it more general, what I depicted here is I'm assuming that we're making predictions at every single time step. All right, so that's the standard approach. This is the retain approach. What's happening here is instead of embedding or encoding your sequence using RNN, we linearly project it into the lower dimensional space, just like feed-forward neural network. We just multiply a certain weight matrix to the input x, and then get vi, and then there's there's an attention mechanism which is responsible for the first question being which visit was important. So, and instead of using a feed-forward neural network, we use RNN instead. So using an RNN, we generate the attention weights for the visit level attention. And then because there was the code level thing, so there's another separate RNN that generates the attention weights for the code level attention. And you can imagine why we're using RNN, because instead of encoding the inputs time for the sequence of x's, x0 to x1 to xt, instead of encoding them using RNN, we encoded them using separate, like independent linear transformation. So we're losing the sequential information there, but here by using RNN on the attention side, we're sort of recovering the lost sequential information again. So two separate RNNs, one for the visit level, one for the code level, and then since you have all the things you need. You have the hidden representation of your visit. You have the attention. You have the visit level attention. You have the code level attention. So you just multiply them. You multiply everything together to get the context vector C here, and then based on that you make a prediction. So the fundamental difference between the standard approach and the retain approach is you look at the prediction pathway from xi to all the way to yi. So when you have xi, and then there's like a path all the way to ii, there's a self loop here. So there's like a nonlinear RNN involved in this pathway. But here there is no linearity. There is no RNN involved in this pathway all the way from xi to yi. So that is why you can completely decompose yi, your prediction, into the contribution scores of individual xi's in every time step. It's because of the preserved linearity in this prediction pathway, this workflow. So that's the core information. That's the core idea in retain. Any question so far up until this point? So after this, I'm gonna jump into more like detailed derivation. So this was more like a conceptual approach. No? All right. So this was like a collapsed or like a merged depiction of the RNN model and the retained model. So there's only xi here, but when we unfold it into multiple time steps, so there's xi to x1 to xi. So yeah, I didn't use t here, I guess. So we're feeding in from x1 to xi being the last time step. And so this is the encoding part. And in the encoding part, what happens is you just linearly embed them. So there's the xi being, of course, the xi will be the multi-hot vector, the binary sparse vector where some dimensions are 1 and the rest of the dimensions are 0. So xi is multiplied to the weight matrix E. This is the embedding matrix, and that's how you get the V. So every time step x1, x2, you get V1, V2. And the next one is the RNN alpha, which is responsible for the visit level attention. So as I said, this is the RNN. So you simply just feed in your hidden representation, the visit embedding, linearly, like sequentially into the RNN. So that's how you get alpha weights. So you use the softmax function to derive the convex weight alphas. So that's pretty understandable. This is a bit more involved, or I guess this is a little less straightforward. Here we're still using RNN, but instead of generating the scalar alpha weights like here, we're generating the vector at each time step. So betas like beta 1, beta 2, beta I are not scalar values, because what we're trying to do here is we're trying to derive the attention distribution for all the codes in each time step. So if you have a scalar value here, then you can't really like treat individual codes differently within each time step. So we need a vector to do that kind of stuff. So that's why beta is a vector. So like beta 1, beta 2, all the way to beta I. And of course, the beta weight, the contents or the values of beta will be different, because we want to focus on different things in each time step, like focus on different codes in each time step. So betas will be different. All right. And then, so once you have the alpha and the betas and the V's, everything, you have everything prepared. So you just simply multiply everything together and then just sum them up. So betas are vectors. V's are vectors. So you do Hadamard product or like a coordinate-wise, piecewise multiplication. You multiply the first dimension of beta to the first dimension of V. You multiply the second dimension of beta to the second dimension of V, and you do that for the entire dimension. Typically, the dimensions we're using is 256 or 128. So it's a piecewise multiplication here. And of course, alphas are scalars. So we just simply multiply the alpha here. And then you're doing this for the entire time steps from 1 to I. So you just sum everything up. And that's how you derive the context vector C for this particular time step. You have done this for x1, x2, and now you're at xi. So you're trying to obtain the ith context vector, and then based on that you make the final. Based on that, you make the final prediction. Based on the CI, you're making a multi-class classification. Right. So yeah, I didn't use binary prediction. I just wanted to generalize to multi-class classification. So you can, of course, switch this to a sigmoid function to make it into binary prediction. Right. So this is the like a forward step, and the reason that we can decompose the contribution scores of individual codes in each time step the justification will be coming right now. So just because like we put everything into we keep this pathway linear, how can we actually answer questions like this, like if your model predicted pneumonia will happen in the next time step, then like 40% will be like chest X-ray will be responsible for the 40% of the prediction. Cough here will be responsible for the 20% of the prediction. Like cough here in the first time step will be responsible for 10% of the prediction. So we're gonna go through why this is possible in retain. All right. So we're backtracking. So from the very last time, the very last step of the prediction where the Y's or the prediction was derived by the context vector. Okay, so there's a question. Okay, so it's just, all right, it's something related to the assignment. Okay. All right, so backtracking from the prediction step and going back to the encoding step. So, all right, so your final prediction, given a context vector, your yi would be described like as a softmax function accepting WCI plus B. So W and B are the final like linear operation, and CI was your context vector. So you can simply replace your context vector with this. So this was what we did to derive context vector. We multiplied everything and then summed up across the timeline, across time steps. So CI now becomes, all right, CI. All right, CI now simply becomes this part. Then, okay, I have to always this. All right. Next step is VJ or VI to be more precise was this EXI. So VI was just a simple linear transformation of your raw input, the sparse binary vector, into the lower dimensional embedding, 128 dimensions or 256 dimensions. So what you do is you simply just okay, so anyway, you simply just replace the VJs into EXJ because of this relationship. And of course, when you do this, I think I could mention this very briefly, like maybe three lectures ago or 4 lectures ago. When you're doing like dot product between the weight matrix and the vector, you can view it as a dot product, but you can also see it as like a weighted sum of the columns of the weight matrix. Well, this won't be a weighted sum because if your values will be either 0 or 1, so it's binary indicator. So anything that has 1, like the cough the cough here will correspond to the first column of the embedding matrix. Fever, blue, Tylenol, green, IV fluid, yellow. So these will be, so EXJ is simply taking the corresponding columns and summing them up, the active columns. All the columns that correspond to the zeros here, they won't take any part in deriving your V, the visit embedding. So you only take the active ones and then you sum them up. So that's what's actually happening in EXJ. And the reason I'm telling you that is because I want to do this instead. So instead of putting EXI, what's happening is you're taking the columns of the active dimensions and then you're summing them up. So XJK is the indicator, 0-1 indicator for the kth code in jth visits. There can be many codes in each visit, typically 40,000 codes to be more precise, like 10,000 diagnosis codes, 20,000 medication codes, another 10,000 procedure codes. So the X would be typically 40,000 dimension vector. And like in each dimension, it'll be either 0 or 1, depending on if that happened in the visit or not. And this here is kind of like the MATLAB way of describing a particular column in the weight matrix. So this will be the kth column and so of course the weight matrix or the embedding matrix E will have like 40,000 dimension, 40,000 columns basically. So okay, so you can see the relationship here, like because EXJ is exactly like summing these up. I'm just like rewriting this as a sum of columns. So R is like your number of dimensions. R would be like 40,000 here. All right, next. So once you've done that, you can put all the terms that are irrelevant to the K term, the K index, you can put them all inside the K sum, the sum over K. So like alpha J, beta J, W. I mean, alpha J and beta J are dependent on the J index, so it can still go in, doesn't matter. And W doesn't have anything to do with any index. It doesn't have to do with J, it doesn't have to do with K. So you can all put them inside the two sums here. So, and then yeah, after that, after you've done that, you put the scalar values. So this is either 0 or 1. Alpha J is the scalar value indicating the importance of the jth visit. Scalar values to the front, and then the vectors and the weights to the right. So this is the weight matrix. This was a vector. This is also a column. So this is a vector. So you can rewrite stuff like this. So what's happening here is just there's a double loop here. So, all right. So there's first loop, which loops over the time steps. There's another loop, which loops over different codes, the 40,000 codes. So you have two for loops basically, and inside the nested for loop, you're just calculating this here. And then after you've done that, you put it through a softmax to get the final prediction Y. Right. So that's why everything can be like the reason that we kept everything linear is because we can do this kind of operation. We just rewrite stuff, and then we can have we can rewrite this as like a nested for loops. All right, so once you've done that, okay, all right, this is always very annoying. All right, once you've done that, because this was a 0-1 indicator, this part here is the contribution. This is coefficient. So this, you can think of this as like a logistic regression for sequences. So there's a contribution coefficient. There's a weight coefficient for each code in each time step, which would be this part. Because as I said, this is either 0 or 1. So if it's 0, then the whole thing doesn't really matter, because of course some things that didn't happen in the jth visit doesn't really have an impact. Things that did happen, like cough, fever, Tylenol, things that happen, they do have an impact, and the impact is this much. So right here, so here, this is the contribution coefficient, the impact, or the impact that I just described, and this is an indicator, 0 or 1. And of course, you can generalize this to not just the 0-1 indicator, but actual scalar value. Like this could be like the blood pressure. So if we're doing blood pressure, then this could be like 120. Then your actual contribution would be this times this. Like the contribution at particular particular code or particular feature, the case feature at jth time step would be the multiplication. But when we're doing like 0-1 indicator, like something did happen or did not happen, then this is your contribution factor. So I hope this is clear, the whole derivation. Any questions so far? I hope that it is very crystal clear why retain is a fully decomposable model, fully interpretable model, because every single code in every single time step, like kth code in jth time step, can have this much impact to the final contribution. Is that clear? Any question? Nope. Okay then, so moving on to the experiments. We still got 7 more minutes. All right, so what I did is so this was a model that I developed like back in 2015 or like late 2015 or early 2016. So, and I was working with a healthcare network or healthcare company named Sutter Health, and I was doing an internship there. So they gave me 33,000 patient records. Did I explain this? I think I did. Yeah, I think I went through this like a couple lectures ago when I was first introducing the RNN. So it's the same setup. 33,000 patients from Sutter Health, and 4,000 of them were cases. 30,000 of them were controls. Like cases and controls. Like these are the patients who did actually have heart failure. These are the number of patients who did not have heart failure. So it's like a 비교군 대조군. So based on these, and of course, as I said, originally each patient, each visit will consist of like 40,000 dimensional vector, because like 10,000 diagnoses go 20,000 medication. I didn't do that in this example because in trying to visualize 40,000 different codes would be like a pain. It would be very painful. So we like aggregated, or we merged different medical different types of medical codes into, basically we reduced 40,000 dimension into 615. What we did is, for example, if there are, like, we can merge type 1 diabetes with type 2 diabetes, and we just merge them into single diabetes. You know, like in Korean, 그러니까 1형 당뇨랑 2형 당뇨는 그냥 다 당뇨를 퉁치는 그런 짓을 해가지고 이제 4만 차원 615차원을 줄였다는 얘기예요. All right, so some reduction in the input space. And the performance ledger is our AUROC, and the competing models were, of course, these models are nonlinear models, so you don't need to care about them. But the interest, what we really want to see is retain is a kind of like you made a sacrifice. You made a sacrifice to keep the X to the Y path linear, and you put all the nonlinearities in the attention part. So we made some restrictions. So you can kind of imagine that there could be like a hit in the performance. Like you're sacrificing some predictive performance and trading that off with the interpretability. So we want to compare art retain with the just simple GRUs, and we made it into a 2-layer GRUs to make the number of parameters like similar. Like number of parameters used in retain and number of parameters used in the RNN would be similar. And this is GRU plus attention. So this is like the typical way of using RNN as an encoder, and then feed for a neural network as an attention function. So these three things are what we are interested. The performance comparison between these three things are what we're after. And you can see that actually they are probably pretty similar in terms of predictive performance. So the vanilla 2-layer GRU has the highest heart failure prediction performance, 87% AUC. But retain is like, it's almost the same, 8705, 8706. It's basically the same performance. And typical, the RNN plus attention, the typical way of using the attention on top of RNN, not that much. It's not doing so well. But again, it's not like there's like fundamental predictive performance difference between these three models. So the takeaway lesson is that even though retain made some sacrifice by making the pathway linear, the decrease in the predictive performance is not that much. It's negligible. And then, as I've shown you in the demo, it is fully interpretable. So it's a pretty good model to use, actually. And to be honest, retain does take some hit in the performance, does show decreased performance when it is applied to some other prediction task, because heart failure prediction is a binary task, so it's a rather straightforward task. So in that case, retain shows like pretty similar performance to the vanilla RNNs. But when you're doing a little more complex stuff, then it does take some hit in the AUC, but not drastically. So it's always a good compromise to make. All right, some interesting stuff before we wrap up the class. All right, so what I'm doing here is, this is not an interactive stuff. It's just that I picked a specific patient and then did some tweaking to the patient. So before we go to the tweaking part, again, the x-axis is the number of days, and the y-axis is the contribution. And these are the visits. So there was a visit in day 0, 50 in like 2 months later, there's another visit, a month later, another visit. So 1, 2, 3, 4, like 10 visits in total. And similar pattern, as the patient, as the time progresses, the patient starts to develop heart-related conditions like CD, dysrhythmia, so 부정맥, CA, 경맥동화, HVD, it's I don't know what this is in Korean. 판막 valve disorder. I don't know what this is. Anyway, so yeah, increasingly severe condition, and then day 354 diagnosed with heart failure. So no question here. And final scores, of course, was 2474 again. It's a rather high score because control patients, like patients without heart failure, they typically have risk score of 0.00001 or something. So 2474 is a pretty significant number. And what's happening here is I reversed the order of the event exactly like in a reverse order. So HVD CD is in the first time step, and like CD CA SD in the second time step. So the reason that I did this tweaking is because I wanted to see if retain is actually considering the temporal information, the sequentiality of the events. And interestingly, it does, because if you look at this is the patient who did not have heart failure, heart-related conditions, and started to develop and then diagnosed with heart failure. But this patient is the exact opposite. This patient started off with severe heart-related symptoms, but then got better and got better and got better. And then as time progressed, like in the later stage, in the later phase, all this patient had was skin disease problems. So the risk score has like drastically reduced from 25% to 9%. So it does truly show that retain does take into account the temporal information, the order of events, which is not the case in logistic regression, where you just sum everything up. And the last bit is a bit more like a exploratory thing. So what I did here is, when the patient started to develop heart-related conditions, I intentionally added like 2 medication codes, antiarrhythmic medication and anticoagulant medications, all to do with like dealing with heart-related conditions, heart conditions. So day 2019, 294, 320, like every single visit where they have heart-related conditions, I added these 2 medications. And you can see that the risk has kind of like decreased, not like drastically like 9%, but still like 24, 25% to 21, 22% is kind of like a noticeable decrease. And of course, we shouldn't use this as like a simulator, because this is not a causal model. This is still an association-based model. So you can't derive the fact, you can't arrive at a conclusion like, hey, if we use if we use antiarrhythmic, anticoagulant, then you can prevent heart failure. That's not what we should do, because that would be the wrong conclusion to derive, because this is not a causal model. But this somehow like kind of indicates like there might be something there, like some relationship between these medications and heart failure. There might be something like negative correlation there. So it's kind of like you can use it as like a pseudo simulator. You want to like, maybe you want to like tweak the days a bit. Maybe you want to take some information out, take some code out maybe, or you can just add some code in, something like that. And that's what you can see in this another demo that I'll show you in the next class. All right. Okay, I guess this is a wrap. So next class we'll go through some visualization demo again, and then wrap up the model-agnostic approach. Any questions so far? Any question for today's material? I hope the retain model was pretty crystal clear. All right, no question? All right then, thank you everybody for attending the class, and I'll see you guys next Thursday. All right, have a good rest of the day, and I'll see you guys again. Bye-bye.